Now let us discuss the case 2 of the ring. So basically this is the same ring of m mass and r radius, but this time rather than finding moment of inertia about this axis which is perpendicular to the plane of the ring, I am going to find the moment of inertia about this axis which is lying in the plane and it is basically along a diameter. So this is the diametrical axis. Now this is the ring. This is the axis which is perpendicular to the ring. We already know moment of inertia about that is nothing but mr square. This is what we needed to find. Let us say this is nothing but ix. I am taking another axis which is along y-axis, and this y-axis is perpendicular to our x-axis. So basically there are two axes, two axes, both are in the plane of the ring and they are mutually perpendicular. If you want to look at the top view, then this is my x-axis, this is my y-axis, and the z-axis is coming out of the plane. So this is my z-axis. So z-axis is like, this is the z-axis. So this moment of inertia about this x-axis, if that is I, then moment of inertia about y-axis is also going to be I due to symmetry. See, moment of inertia depends on what? The mass and the distance of mass from the axis. So here the mass of the about x-axis is distributed like half the ring is over here and half the ring is over here. But about y-axis, again the same type of distribution, half the mass and half the mass is lying at this distance. So moment of inertia about this axis which is I, then moment of inertia about this axis should be same as I. So here the Ix and Iy, both I can assume as I. And now I am applying perpendicular axis theorem. So what does perpendicular axis theorem says? Iz is equal to Ix plus Iy. So I already know Iz. So I'll say Iz is equal to Ix plus Iy. And what is Iz? This is mr square. This is I and this is also I due to symmetry. And that gives me 2I is equal to mr square. And that is going to give me I equals to mr square by 2. So if we talk about this axis, then moment of inertia about this axis is nothing but mr square by 2. This is the moment of inertia about this axis, while we already found that moment of inertia about this axis is mr square. So now let us discuss our next case. So this is again, we are going to talk about ring only, but the axis is different. So just now we found that moment of inertia about this axis was mr square by 2. Now see, this is an axis which is parallel to another axis. So this axis is another axis which is just touching the circle, touching the ring, and it is lying in the same plane. So this is parallel to that diametrical axis. So this is so here we are going to apply parallel axis theorem. To apply the parallel axis theorem, what do we need? We need two things. One is the ICM. So here I am going to call this axis as ICM. This axis is passing through center of mass because center of mass of the ring lies at the center, right? And the distance. So distance between these two axes is nothing but r, that is equal to the radius itself. So I will say that this I, moment of inertia about this axis is nothing but ICM plus md square. ICM I already knew that it is mr square by 2 plus mass of the object which is m and distance which is r, so r square. So mr square by 2 plus mr square gives me 3 mr square by 2 or 3 by 2 mr square. So this is the moment of inertia about this particular axis. Let us discuss one more case where this is an axis which is perpendicular to the plane and it is just touching the our ring. So when we need to find this, here again I already know about this axis. So this is an axis which is parallel to our given axis and passes through center of the circle, center of the ring, right? So that is going to be, we already know this is mr square and I am going to call it ICM. ICM is which axis? That axis about which passes through center of mass and it is parallel to our given axis. So if when I have to find this, for that I can apply parallel axis theorem again. So I will say I is nothing but ICM plus md square. So what is ICM in this case? ICM is nothing but mr square plus md square, which is another mass of the entire ring, which is again m. Distance between these two axes is nothing but r again, so it is r square. which gives me 2mr square. If we summarize the entire thing in one picture, then we will say that, so moment of inertia initially first was this axis. So it was mr square. Moment of inertia about this axis is 2mr square. Moment of inertia about this axis is mr square by 2. And moment of inertia about this axis, which is basically touching a tangential axis in the plane of the ring, is 3mr square by 2. So as you can see, depends on the axis. For the same object, we have different moment of inertia. It depends on what is the axis of rotation. We'll tell moment of inertia as per that axis. Let us discuss the next case, which is a disc. So for a disc, I am taking a disc which is having m mass, r radius. Now, this is a continuous object again. To derive the formula for moment of inertia, I am going to, this is an axis which is perpendicular to the plane of the disc and passes through its center. So what I am going to do is, I am going at r distance, and now I am going to take a ring. The ring is having a width of dr. So I need to write the mass of that particular ring, and that is our dm. So what is the dm? I will say here, for a disc, mass lies over an area. And I will say total mass divided by total area. What is the area of the entire disc? I will say it is a 2D object, so mass lies with area, right? So an area is nothing but pi r square is equal to required mass. The mass of this ring, elementary ring, is dm, which we need to find, divided by the area of the ring. How much is the area of the ring? You can take this ring, you can expand that, and eventually length of the ring becomes 2 pi r, while the width is nothing but dr. So I'll say treat it as a rectangle, and the area is going to be 2 pi r dr, length into width. And when you solve it, pi is gone, and you get your dm is equal to m by r square, this 2 and r dr. So this is my dm. Now I just need to apply the formula. I is nothing but integration dm r square. I went to r, take an elementary ring, and now I know the entire mass is lying at r distance only. So I can utilize that integration. What is dm? Dm we already found. It is 2m divided by r square r dr times this r square. So it is going to be r cube. What will be the limits? The small r is changing all the way from 0 to capital R. Once that changes, we'll get these small rings will cover the entire portion and we'll get a disc. So now the limits are 0 to capital R. We just need to integrate it now. So that is 2m by r square. That is a constant quantity. Integration of r cube is r raised to 4 by 4. Put the limit and you will get 2m divided by r square, r raised to 4 by 4. Cancel whatever you can. So this is 2. This is cancelled and we'll get a square. So answer comes to be mr square by 2. So for a disc, the axis which passes through its center of mass and perpendicular to its plane, the moment of inertia is given by mr square by 2. Now we are going to utilize this and the theorems, perpendicular and parallel axis theorem, to get the moment of inertia of various axes about the disc. So let us see the next scenario. We already know that about this axis, which is perpendicular to the plane of the disc and passing through its center, the moment of inertia is given by mr square by 2, which we just derived. Now moment of inertia about this axis. Again, I am going to do the same logic which we did with ring. So this is the top view of the disc. I'll say this is a disc. If moment of inertia about this axis is I, then moment of inertia about this axis is also going to be I due to symmetry. For this axis, half the disc. For this axis, half the disc lies above and half the disc lies below. And for this axis also same thing. Half the disc is lying over here and half the disc is lying over there. So this is the same scenario. So moment of inertia must be same. So I'll say moment of inertia about this axis, which is perpendicular to these two itself, like the z axis itself. If this is Ix and Iy, I am going to say Iz is nothing but Ix plus Iy, where this is my x, this is my y, and z is out of the plane, which is this axis. So this is my z axis. We already know this is my IZ. And once I put the value mr square by 2, then this is also I and this is also I. So I can solve for I. I'll say 2I is equal to that and I equals to mr square by 4. So this is the moment of inertia about an axis of the disk, which is basically diameter. Now, let us summarize this entire thing. Moment of inertia about the disk, this axis which is perpendicular to the disk and passes through its center is given by mr square by 2, while moment of inertia of the disk about this axis, which is also a diameter of the disk, is given by mr square by 4. What is the m? M is the mass of the disk and r is the radius of the disk. Let us discuss the next situation where we want to find the moment of inertia about this axis. This axis is parallel to diameter. So I am making a diametrical axis. So this axis is the one which we want. Let us say this is I. Then I draw a parallel line which is basically passing through center of mass of the disk, which is center of the disk, and this is I am going to call ICM. The distance between these two is nothing but that is radius of the disk. And when you do that, let us apply parallel axis theorem over here. So I'll say I equals to ICM plus MD square. So this I, which I need to find, ICM, which I already know that it is nothing but mr square by 4 plus mass of the disk, which is capital M, and distance, which is nothing but r, so mr square. That is going to give me 5 by 4 mr square. This is the moment of inertia about an axis which is basically parallel to diameter and in the same plane, right, passing through its tangent, like it's a tangential axis which is parallel to its diameter. Now let us discuss the last case where we need to find the moment of inertia about this axis. This axis is basically the axis which is parallel to this axis, which is perpendicular to the plane of the ring and passes through its center. And this is the axis which we want. So moment of inertia about this axis, let us call it I. Here I am calling this as ICM because that is passing through center of the disk, and parallel to that, again we are going to apply parallel axis theorem. So distance between these two is nothing but r, mass is m. So let us apply I equals to ICM plus MD square. So ICM is nothing but mr square by 2. This is the one which we derived already. And what about mr square by 2? What about the mass? Mass is capital M and distance is nothing but r square. That gives me 3 by 2 mr square. Again, let us summarize all these scenarios in one go. So I will say that this is the disk. We have learned about 4 cases. This is the disk and we are talking about this axis. So this is mr square by 2. Second case was this is the disk and we are talking about a diametrical axis. So moment of inertia is given by mr square by 4. Third scenario was this is the disk and I am talking about this axis which is basically parallel to this axis. So moment of inertia is given by 3 mr square by 2. And the last situation is this one where this is the disk and we are going to talk about this axis which is parallel to this axis, which is like in the same plane but passes through, which is like the touching it. So this is a tangential axis and moment of inertia is given by 5 by 4 mr square. And this is all the disk cases. Let us discuss our next situation. So next object is annular disc. So annular disc is basically a hollow disc. So you don't have mass, any mass over here, and the inner radius is R1 and outer radius is R2. So one option is to get, see, I am telling 2 ways to get the moment of inertia about this particular axis. So one way is you integrate. So you'll say integration, it is dm r square. Same thing I am doing, which I did for the disk. I am going at r distance and taking a ring. So what will be the dm? The mass of that ring is going to be the total mass divided by total area. But the area is what? Pi r2 square, the outer radius minus r1 square. So this is the total mass upon total area into required area. This is 2 pi r dr. So we can cancel out pi and then we get the value of dm and integration. Dm is nothing but m divided by r2 square minus r1 square. And then we have 2r dr, so 2r dr. And here there is a r square, so we get r cube. So what will be the limits? Limits are going to be r1 to r2. Put the values and integrate it. So 2m divided by r2 square minus r1 square are going to be as it is, because they are constant, they will come out, and this will become r4 by 4. So when you do that, you get r, after putting the limits also, so you get r2 raised to 4 by 4 minus r1 raised to 4 by 4. And this is like a square minus b square. I am going to apply the formula a plus b into a minus b. So 4 you can take common and this will cancel that out. So you will be left with 2. This 2 I am taking out. So it is m divided by 2 r2 square minus r1 square. And here we are left with r2 raised to 4 minus r1 raised to 4. That is going to give me r2 square minus r1 square, a minus b into a plus b. So r2 square plus r1 square. It is the r2 square, right? So here I can cancel this entire thing, and eventually the moment of inertia what we get is m by 2 r2 square plus r1 square. So for the entire disk it was mr square by 2, but here the different situation is there. So we can't say mr square by 2 minus mr square by 2, where 1 r is the outer radius and 1 r is the inner radius. We can't apply that because that is valid when m is the mass of entire disk. Let us do one more situation, like one more alternative way to calculate the same thing. So here what I am going to do is, I am going to say that moment of inertia is a scalar quantity. So we can add, subtract. So I'll say moment of inertia about this axis of this entire disk. This entire disk is nothing but the moment of inertia of this disk minus moment of inertia of the inner disk. So outer radius is like my R2 and inner radius is like my R1. So when I subtract the moment of inertia, I'll get the moment of inertia of this thing. So when you subtract outer and when you subtract the inner one from the entire thing, you will be left with annular disc. To do that, what I am doing is, I need a mass, because I know the formula is mr square by 2, but I need mass of these individual things. So see, capital M is not the mass of this one or this one. Capital M is the mass of this entire thing. So I am going to say, let us say that mass per unit area is sigma. So here in this case, so I will say sigma into pi R2 square minus R1 square. That is like mass per unit area, and the area of this annular disk is going to give me m. That is the first relation which we can get. What is the mass of that? I am calling it m2. So mass of this is nothing but sigma into pi R2 square. And what is the mass of this? I am calling it m1. That is sigma into pi R1 square. Right? We have been given m and R2 and R1. So we need to get our answer in terms of that. So I'll say moment of inertia of this one is nothing but moment of inertia of this, which is, what is the moment of inertia of a disk? It is mr square by 2. So it is going to be m2 R2 square by 2 minus moment of inertia of this, which is m1 R1 square by 2. We need to put the values of m2 over here because other things are already known. So I am saying it is m2. What is m2? m2 is sigma pi R2 square. Sigma pi R2 square times R2 square. So which will make it R2 raised to 4 divided by 2 minus m1, which is sigma pi R1 square times R1 square, which is R1, which will make it R1 raised to 4 divided by 2. Take things common and you will know that sigma pi is there in both the terms, divide by 2, and it gives me the R2 raised to 4 minus R1 raised to 4. And again, I need to put the value of sigma pi using this equation. So what is the value of sigma into pi? That is nothing but m divided by R2 square minus R1 square. And put the value, substitute this value all the way in this. So what will be the final answer? Moment of inertia about this is nothing but sigma pi by 2. Sigma pi is that. So m divided by 2 R2 square minus R1 square and into R2 raised to 4 minus R1 raised to 4. So R2 raised to 4 minus R1 raised to 4 And again, you can cancel that out and you are left with R2 square plus R1 square. So finally, moment of inertia comes to be M R2 square plus R1 square by 2. And this is going to be our answer. So this is another way to do the same thing. Now, let us discuss hollow cylinder. So if we have a hollow cylinder, this is a hollow cylinder having M mass. Hollow cylinder is like a shell. The mass is not lying in this region. The entire mass is lying at the boundary. So this is the hollow cylinder which is having M mass and R radius. I have to get the moment of inertia about this particular axis, which is also the axis of the cylinder. Now, see, to do this, what I can do is, I can compress this entire cylinder. When you compress it, what will happen? This is the axis. When you compress, it becomes a ring. And in the process, have we changed the distance of any mass from the axis? Answer is a no. See, when you were compressing, this mass was moving down. This was moving down. So all the masses, they were moving parallel to our axis. And when they move parallel to our axis, the distance of any dm from this axis was r and will always remain r if you compress it. So moment of inertia does not change. And when we say it is a ring, the mass is m and radius is r. So we will say the moment of inertia is nothing but mr square. So moment of inertia of a ring or a hollow cylinder is basically same. So there are various cases. So if we already know about moment of inertia of the hollow cylinder about this axis, I need to get the moment of inertia about this axis, which is basically a tangential axis of the cylinder, and it is parallel to the axis of the cylinder itself. If you want to get that moment of inertia, this moment of inertia is the required thing, then this moment of inertia will be called ICM, because that is passing through center of mass. I can apply parallel axis theorem that is valid for 3D objects as well. So I will say I equals to ICM plus MD square. What is your ICM? ICM is this moment of inertia about this axis, which is same as the ring. So mr square plus mass is m. And what about this distance? Distance between these two parallel axes is basically r. So I will say it is mr square, and moment of inertia about that particular axis is coming to be 2mr square. Let us discuss the next situation. So next situation for a hollow cylinder is the moment of inertia about this axis. So this is an axis which is basically perpendicular bisector of the hollow cylinder, but hollow cylinder is a 3D object. Now here the moment of inertia, the derivation we are not doing, but there is a trick to remember it. So moment of inertia is given by m L square by 12 plus m r square by 2. This is the formula for moment of inertia about this axis of a hollow cylinder. It is like perpendicular bisector. Now here is the thing, this is how you remember it. This hollow cylinder, see about this, I can say that it is nothing but it is like a rod plus this axis, it's like this is a ring and this is a diameter. So I will say that find the moment of inertia about this axis, which is nothing but ml square by 12. We already applied that formula, plus moment of inertia about a ring about diametrical axis, which is nothing but mr square by 2. So this is going to be the formula for moment of inertia of a hollow cylinder about an axis which is its perpendicular bisector. It's like perpendicular to its axis and it bisects the cylinder. Cylinder is having L length, R radius and M mass. Now the last situation is moment of inertia about this axis. See, we already know moment of inertia about this axis. Here I have to call this as ICM because this is passing through center of mass and it is parallel to our given axis, and this is the thing which I need to find. So again we can apply the parallel axis theorem. I'll say I equals to ICM plus MD square. So ICM is nothing but moment of inertia about this axis, which is like the rod plus the diametrical axis of the ring, which is mr square by 2. This is the ICM plus m and d square. What is the distance? Distance between these two axes is L by 2. So I will say L by 2 whole square, and at the end this ml square by 12 plus this ml square by 4. What does that gives us? That gives us I can take 12 common, and this is basically ml square, and this is ml square by 4, so 3 ml square, so that gives me 4 ml square and plus mr square by 2. And now you can say it is 3. So it is ml square by 3 plus mr square by 2. Again, when you think about this axis, this is like a diametrical axis for the ring, and this is like for rod, it is the axis which is passing through its edge, and passing through its edge, the moment of inertia of a rod is given by ml square by 3. So again, you can say it's the addition of this and basically for the rod. So this is like the addition of the rod and this axis plus the ring and this axis. So that is what the moment of inertia is. Let us now discuss the solid cylinder. So this is a solid cylinder having m mass, l length and r radius. So here you can here we are finding the moment of inertia about the axis of the cylinder itself, and this is a solid cylinder. So what I am doing is I am doing again the same thing. You can compress. So while you compress, what happens with any of the small mass dm which was lying at r distance? So this mass basically transferred like this. So the distance from the axis is never changing. It was always r. So when you compress, no mass is changing, the distance from the original axis, and when that happens, we'll say moment of inertia does not change at all. So eventually what will it become? It will become a disc of same radius and same mass, and we are talking about this axis. So whatever is the moment of inertia of the disc about this axis is the same as moment of inertia of this solid cylinder about this axis. So what is the moment of inertia? Moment of inertia of a disc about an axis which is perpendicular to its plane and passes through its center is given by mr square by 2. And this is the same thing. The same moment of inertia is going to be about this axis as well. So this is also mr square by 2. Now you'll say the length of the cylinder does not matter, because whatever is the length, the mass is distributed. See, the distance, the actual distance which matters is only the distance from the axis. So here this L is not going to define the distance from the axis at all. Let us do the next case where we have to find the moment of inertia of the same solid cylinder, but now about an axis which is passing through its edge. So for that, I'll take another parallel axis which is passing through center of mass as well, and I will call that ICM. And now this is the one which I need to find. This I already know. This I have to find the distance between these two axes is nothing but r. So I will say I'm going to apply the parallel axis theorem, which is nothing but I is equal to ICM plus MD square. So what is our ICM? ICM is nothing but mr square by 2 plus MD square. So mass is m and distance is basically r, so mr square. So that is going to give me 3 by 2 mr square. So moment of inertia about this particular axis is 3 by 2 mr square for the solid cylinder. There are two more cases. One is this, which is perpendicular bisector. So about this, again about this, I will say that treat it as a rod, an axis which is passing through the middle, and treat it as a disc. Since this is a solid cylinder, so this will be a disc, not the ring, and about this axis. So moment of inertia is going to be moment of inertia of a rod about its perpendicular bisector, which is ml square by 12, plus the moment of inertia of a disc about its diametrical axis, which is mr square by 4, and that is going to be the moment of inertia about this axis for a solid cylinder. Now one more case where this axis, rather than passing from middle, it is passing through the edge. For that, again I am treating it as a rod plus as a disc. So for the rod, the axis is passing through the edge, and for the disc it is the diametrical axis. Now I will say the moment of inertia is nothing but moment of inertia about this, which is ml square by 3 plus the moment of inertia about that, so which is again mr square by 4. So this is going to be the moment of inertia about this entire thing about this axis. Now let us discuss the rectangular plate. Now rectangular plate, this is a rectangular plate having L length and B width. I am giving you a top view. So if it about the top view, then this is the L length and B width. So here I am going to talk about different axes. First axis is this one. So when I have to find the moment of inertia of this rectangular plate, this is a solid rectangular plate. So about this axis, what I am going to do is I am going to compress the disc like this. When that happens, again, these masses, they move like this. So when that happens, the distance from the axis is never changing. So we can say moment of inertia does not change, and the end result is going to be just a rod, a negligible thickness rod having width length as b, and this is the axis which we wanted. So this is like the axis passing through the middle. So moment of inertia is given by ml square by 12. But what is the length? Length is b. So mb square by 12. So this is going to be the formula about this axis. So moment of inertia about this axis is nothing but mb square by 12. Let us discuss what happens if I have to find the moment of inertia about this axis. In that case, you can compress your rectangular lamina or rectangular plate like that. So now the mass does not change about the axis. Any distance of any mass does not change from the axis, and when that happens, this masses moves like that. So no distance is changing. Now this becomes a rod again of L length, and moment of inertia about this axis is given by ml square by 12. So moment of inertia about this axis is given by ml square by 12. What if you have to find the moment of inertia about this axis? Now this is a 2D object. These two are in the plane of the object and basically perpendicular to, these are two perpendicular axes, and this is a perpendicular which is perpendicular to both, right? So this is going to be my Ix, Iy and Iz, and I will say Iz is nothing but Ix plus Iy. So ml square by 12 plus mb square by 12. So moment of inertia is going to be m by 12 L square plus b square. So that is going to be the moment of inertia of a rectangular plate about an axis which is perpendicular to its plane and passes through its center of mass. So next object is the holosphere. So moment of inertia of a holosphere is the next thing which we are going to do. So we have a holosphere having m mass and r radius. Now about this is a holosphere, so it is a spherical shell. So moment of inertia of this about this axis is given by 2 by 3 m r square. M is the total mass and r is the total radius. So this is the thing. Derivation of this we are not doing. Now next, if we have to find the moment of inertia of the same holosphere about this axis which is passing through its tangent, it is a tangential axis. We already know this moment of inertia is 2 by 3 mr square, and this is I which we need to find. So I am calling it as ICM because this is passing through center of mass and this is parallel to it, right? So we are applying the parallel axis theorem. So I'll say I is equal to ICM plus MD square. This is I which we need to find, and now I will say ICM is 2 by 3 mr square plus mass is capital M. And what is the distance between two parallel axes? It is same as radius of the sphere, so plus mr square, which gives me 5 by 3 mr square. Next object is a solid sphere. So solid sphere, again an axis which passes through its center. Moment of inertia about that axis is given by 2 by 5 mr square. And if we have to find the moment of inertia about the same solid sphere and about an axis which is passing through its tangent, then again I am doing the same thing which I did with holosphere, and moment of inertia about this axis is 2 by 5 mr square, and I am going to call this as ICM because this axis is passing through its center of mass and it is parallel to our given axis. So I am applying parallel axis theorem. So this is the I which is missing. So I am going to apply parallel axis theorem. I is equal to ICM plus MD square. So ICM is 2 by 5 mr square plus mass is small capital M of the holosphere, solid sphere, and r is the radius, which is also the distance between two parallel axes, and that gives us 7 by 5 mr square. So this is the formula for moment of inertia about this axis. Now let us recollect all the things. So if we have two types of sphere, if it is a solid or hollow sphere, For holosphere, the mass is situated in this region. Now, since the mass is lying at the perimeter or periphery, we will say that it is having mass is situated more distance. While in the same situation, if we are talking about a solid sphere, then mass is lying in this entire region. So here mass is more closer. Mass is more closer to our axis, so moment of inertia has to be less. So that's how you can remember this is 2 by 3 mr square, while this is 2 by 5 mr square. If you apply parallel axis theorem, then you can get the moment of inertia about these two axes as well. So you just need to add mr square in these two ICM.